Before we look at an application of exponential functions, I have a couple of questions first. What is 4% of $5,000? This is a pretty easy computation where you take 5,000 and you'd multiply it by, well, actually 0.04 because you have to convert it to a decimal, and your answer is 200. That's what this is equal to. In fact, $200. One interpretation of this answer is, if you happen to have $5,000 and you are earning 4% interest, let's say every single year on this amount, the total interest at the very end would be $200. This is the interest. But if you need to know the total amount of money that you have, it's not just the interest, but it's the $5,000 that you started with. So if you need the total amount of money, you'd have to throw in this extra step of take your $5,000, add in the $200 interest to give you a grand total of $5,200. There's a way to do this in one step, and that's the answer to this question over here. What is 104% of $5,000? So same idea, you would take 5,000, but you wouldn't multiply it by 0.04, you would multiply it by 1.04. because you'd have to move this decimal 2 places to give us this value here. Okay, this time, when you multiply the two numbers together, you get 5,200. That's $5,200. So this tells you just the interest, but by putting a 1 instead of a 0 in front of the 0.04, it does all of this work in one step for us. Now on to our application of exponential functions, and I want to start here with the problem focusing here. So the question is, if you had $5,000 and you invested that money into some account that earned 4% interest applied once a year, which is the same thing as saying compounded annually, this account is going to grow in value. Well, how much money are you going to have after 8 years? To answer this problem, I'm going to use this above formula. Here, B of t represents the balance of the account after t years, B sub 0 represents the amount of money that you start with, and R represents the interest that you earn each year. So let me write those things down. B sub 0 is the starting value, $5,000, and R is that 4% interest. Let's plug all this stuff into the formula. B of t, the balance after t years, is equal to 5,000 times 1 plus 4 divided by 100, all raised to the power of t. If we look at what is inside the parentheses, we have 1 plus, taking 4 and dividing it by 100 converts it to a decimal, and so that's 1.04. I can now write my formula even more simply as 5,000 times 1.04 to the power of t. So this is an exponential function. The variable is in the exponent, the base is 1.04, and because the base is greater than 1, this exponential function should be increasing over time. That's a good thing. That means we're going to multiply 5,000 by an exponential function that is increasing, meaning the value of your account is going to grow. It's not going to grow very fast, but it will increase over time. So now on to answering this question. How much money is going to be in this account after 8 years? This is a very simple thing to do. You can basically take t equals 8 and substitute it into this equation and then compute the y value. Let's do this in our calculators. In place of y1, I'm going to enter this function. The difference is the variable is going to be an x instead of a t, but it's going to work the exact same way. I will enter 5,000, parentheses 1.04, use the caret symbol to get an exponent, and then place my variable x. I can now go to my table of values. I can choose anything that I want for my x value to solve for the corresponding y value. So I'm going to plug that in and see what I get. Okay, I just entered my equation. When t equals 8, that means I'm just putting an 8 in place of x. So I'll put that into my table. And the value I get back is 6,842. And it says 0.8. I'll just put an extra 0 at the end to give this as a decent approximation. But this is my answer. The balance of the account after 8 years is $6,842.80. For this problem, there was nothing special about me choosing 8 years. Once you have a formula, you can put any value that you want in place of x. So maybe you could even ask the question of, well, what if I waited a little bit longer? What if I waited for 15 years? I'm expecting the account is going to be a larger value this time, but you can just go to your equation, type in 15. Here we get $9,004.70. So that's the balance of this account after a total of 15 years. So that's not really growing very fast for such a long period of time. In fact, it hasn't even doubled in value over 15 years, but that is how much money that would be in the account. So one last thing to consider is why this formula works. And to do so, I'm just going to choose a couple of other values to put in place of t, like 0 and 1, for example. What would the balance of the account be if no time has elapsed? Like right at my starting point. That should be equal to the amount of money that you first put into the account. If you go to your calculator and put 0, it gives you 5,000. So that's actually a good thing. That should match up. That's the amount of money that you begin with. But it makes sense in your formula. If you put 0 in place of t, this number to the power of 0 is all equal to 1, and 1 times 5,000 gives you 5,000. That's good. Well, what about after 1 year? Okay, when I check this, the value is 5,200. Okay, that's a good thing. That also makes sense. After 1 year, if you put 1 in place of this t, that is 5,000 times 1.04, which, as we saw before, takes the $5,000 and then puts in that 4% interest and adds them together for you. So every time you increase the exponent by 1, you're simply multiplying by another factor of 1.04, which will take you from year to year to year. And that is it for this example.